8.6, National Electric Code, voltage drop recommendations. Let's get our code books out. Let's go to 210.19. And there's an informational note. I don't think we talked about this, so let me just... I want to delete that because I want to be able to talk about it with you in class and not have it already highlighted. All right, 210.19. One thing we have to be aware of, first of all, let's get back up here. We are in 210, and Article 210 covers...
Branch.
Come on, baby. Let me highlight that, just so we're together. So we're talking about branch circuits. Okay, got that. Now I want to go over to 215. So let's get to 215. And I want to highlight 215. That is 220. So I need to go back. 215. Here we go. 215. I'm going to highlight Article 215. All right. I'm going to go back over to 210.19, which is in branch circuits. And in branch circuit, minimum ampacity size, A, is not more than 60 volts. And I want to go to, you know what? This is very interesting. How often do you see a code rule? Matter of fact, I think it's the only code rule I've ever seen that starts off with 4 informational notes. They're like, oh, listen, before you get going here, hold on. Oh, don't get too excited here. Number 1, 310.15 for ampacities of conductors. 2, motors, minimum protection device. 3, temperature limitation. I can think of a lot of rules that you could add here if you're going to start that kind of a list. What about bundling? What about continuous loads? I mean, like, what else are you guys doing here? So I think that doesn't really add a whole lot. But let's get into the informational note, too. And, John, what's the deal with informational notes? Do I have to, are these enforceable things?
No.
No, it's just like, hey, information. Matter of fact, let's do that. Let's go to the code that talks about, anybody know what code rule talks about informational notes that tells us what's going on?
I think it's in 110. True.
To the beginning.
90.
So 90.5C?
Yeah.
90.5, so let's highlight that. Exactly right, Ken. 90 dot, come on, baby, you can do this. Nope. Doesn't look like I'm going to be able to do it. All right. So 90.5 is mandatory, permissive, and explanatory. C says explanatory material, such as references to other standards, references to related sections of this code, or information related to a code rule is included in this code in the form of an informational note. So explanatory material is contained as informational notes and are not enforceable as requirements. So we're going to go back over to 210.19. Somehow I messed that up. 210, oh, I see what it is. 210.19. Okay. And we're going to then go over to informational note 4. And can we agree, team, that this is not a requirement?
Correct.
Because it's informational note 4. Okay. Voltage drop. 3%. And then
5%.
okay, both feeders and branch circuit is 5%. Oops. Both feeders and branch circuits. I don't always, you know what you could do, John? You probably highlight the whole thing and then underline in red. I don't have that ability with right now. So exceed 5% for feeders and branch circuits. Okay, so branch circuits cannot exceed 3, is that right?
Correct.
And feeders and branch circuits combined cannot exceed 5. And it says, see informational note. Here's an informational note. I've never seen that. Here's an informational note telling you to see an informational note. That's kind of cute. So let's go to 215.2a. 215.2a. All right. 215-2a. This one they didn't put in the beginning. They just put it right down. Here it is. So now I'm in feeders. And this is not a requirement, so I'm going to highlight informational note. And voltage drop is limited to 3%. And both feeders and branch circuits are limited to 5%. Okay, guys? So let's kind of take a look at the slide. So the NEC has a recommendation, not a requirement. Now, a lot of people think that voltage drop is a requirement, but it's not a requirement in the National Electrical Code. There are energy codes that specifically have it. Mario, are you familiar with the energy code?
Yes.
Can you tell us, because you're an inspector, so tell us about the energy code.
It's 2% on the actually service-owned customer, service conductors and feeders, and 3% on the branch circuits.
Say it again to me.
In
What?
the energy code.
And the energy code is what?
It's the service-owned conductors,
The services are
2%.
2%.
And feeders, 2%. 3% for the branch circuits.
okay. Services 2, feeders are 2, branch circuits are 3. So that gives me 2 and 2 is 4 plus 3 gives me 7. Right? You guys agree with that? So when I figure out my branch circuit conductors, my voltage drop that would be permitted would be 7% of the voltage source. So when I get to my receptacle, that voltage at that receptacle could not be anything less than 2% on the service, plus 2% of the feeders, plus 2%, plus 3% of the branch circuit, which would be 7%. Is that true?
No. It's 5% is the total threshold.
Does it say that? You didn't
No, it
say
doesn't
that.
say that. It doesn't say that, but
Well,
it's
then why would you get 5%?
because it's 2% on the service-owned
Gotcha.
conductors
Right.
and feeders.
You said, I thought you said
And
2% on the
feeders.
service and 2% on the feeders.
Yeah.
All
No,
right,
no,
so
no.
it's 2% on the servers and feeders,
And
it's
3% on the branch
I'm sorry, I
circuits.
misunderstood it. Okay, so therefore, okay. All right, so we have some energy codes. Is that an energy code? Is there a name, a number, a description?
Yeah, it's we're in Florida over here. It's the Florida Building Code Energy
Okay,
Code.
All right, then we'll move on. So here's an example that, okay, here would be, I'm not sure why we have voltages here at 202 and 197. All right, I'll have to change the slide. These numbers don't make any sense. The intent is that the voltage at the equipment should not, it's a recommend, I guess I'm trying to say that
was
if you had
208 coming
202
in.
here from a 208 volt system, and if you ended up having 198 here, that would be fine because the equipment has a marking rating from 208 plus or minus 5%. And actually, this equipment marking rating should be plus or minus 10%. So if this equipment's rated 208, it can go up to whatever 10% of 208 is, and it can go down to 10% of 208, which I guess probably like 180 something.
220.
So that would be the range here, and I think I'd rather kind of use this more of like maybe 240 rather than 208 for a piece of equipment like that, especially since it's being connected to only two-phase. So if I had to do this again, guys, do me a favor. I got a 240 volt piece of equipment. I got minus 10%. What would be the minimum voltage the equipment is rated for? The equipment.
226.
What you're going to multiply by what, John?
240?
240 times? 90%.
You said,
.9.
Yeah,
90%.
And what's that come out to be?
216.
So 240. So the lowest 216 for a 240 volt system.
Yep.
Oh, I take that back. It's not 240 volt rated.
208.
No, it's not two. I'm saying I'm going to make an example that I would rather it be. 240 volt systems. What is the rating of the equipment?
230.
Right.
230.
The equipment rating is not the same thing as the nominal rating of the system. So this would be a 230 volt rated piece of equipment. 90% of that, I'm going to change this graphic for the textbook. 90% of 230 is
207.
207. And it could be plus 10% of 230, and it's going to be
253.
253.
253.
So that's my voltage range. 207 to 253 for a piece of equipment rated 230 volts. And then, of course, the voltage in that, the minimum voltage for the equipment rating itself would be 207. So we'll just change this graphic a little bit. The point he was trying to make is it's informational note. It's not a requirement. All right, so let's go to note one. Eric?
yeah, Mike, concerning that informational note, at the bottom of the informational note, it says,
Hold on. Are you talking about branch circuits or feeders?
both, but branch circuits. I'm looking at branch circuits.
Okay.
It says,
Oh, one second. I'm sorry. I hate to do this, but I'm just getting excited. Take a look at the feeder informational note. 2. It doesn't have a C informational note, C21019. It actually has what? Its own separate informational note about branch circuits. You remember that one? Mm-hmm. Where in the branch circuits, right? Hey, by the way, here's an informational note telling you to see an informational note. Now, here's an informational note, but the information note seeing the other information note is not combined within one. It's simply see the other
separate
one.
one.
Okay, go ahead.
okay, the last few words in that sentence are to provide reasonable efficiency of operation.
Right.
Okay, so some people can get hung up on the 3% voltage drop, but I'll give you an example. For if 120 volt circuit, 3% voltage drop to a branch circuit would result in 114, an end voltage of 114. Well, if my equipment says that it'll operate at 108, I'm fine. I have satisfied the reasonable efficiency of operation.
You're absolutely right. And what Eric is saying is that if you had a piece of equipment rated 115, the manufacturer's already established the voltage that it can operate in, and that's going to be 10% of 115 minus, which would be 90% of 115, or 110% of 115. And if you operate within that, we're not even discussing this reasonable efficiency of operation because we are in the range that it's supposed to be rated.
Right.
It's only if you started to get below that that you're not in the rating of the equipment. Like, well, you know what? You might have some problems with that equipment. Brian?
Well, I just actually was thinking about that, and as we have progressed towards having everything on switching electronic power supplies, the way they work, they actually are not using the full voltage anyway. They just are knocking it down and turning it into a DC. So the voltage ranges are much broader than they used to be. There's some things that'll operate down to 100 volts or 90 something volts. And then you can plug it in Europe all the way up to 250 volts, the same exact thing without ever flipping a switch, and it doesn't care. So I think this is actually a really good thing to bring up right here.
Is when, I guess the key is, if the equipment is not being operated within its rating,
Right.
then we have a problem. Then it might not perform the way it's supposed to perform. But if you're putting in between 100 and 250 volt piece of equipment, it doesn't matter what the voltage drop is.
And it doesn't care, and it doesn't affect efficiency on that equipment.
Okay, let me ask you guys a question here. Help me out here. Today's equipment, office equipment, lighting, is voltage drop really an issue?
No.
Electronic computers, power supplies, almost every single thing's power supplies. The lighting is all electronic. So voltage drop today, but would you, well, let's not go there. Today, we're not. Now we're talking about equipment. Energy code is not talking about equipment.
No.
Energy code is talking about what? Losses of conductors.
Yeah.
Power loss of a conductor. And I'm going to ask you guys a question that maybe a little later. Okay, let's go on. All right, so looking at the slide, 210.19a note 4 and 215.2a1 says that the branch circuit maximum was 3%. It says the maximum for the feeder is 3%. And it says the combined maximum between the feeder and the branch circuit, it shall not exceed 5%. Okay? Same thing what you're saying the energy code says.
Yeah.
Except the energy code says only feeder 2%, branch 3,
3%.
not the combination of both.
Yeah.
All right? So let's take a look at an application. So effectively, the voltage drop from the source all the way down over here, the 5% of that would equal 6 volts. So 6 volts from 120 gives me 114. My brain is thinking this for the energy code. If I can get 2% voltage drop on the feeder service and 3% on the branch circuit, I don't know, do I use 240 or do I use the equipment rating, which is 230? And then therefore my voltage drop would be 5% of 230, which would be 95%. And so the voltage drop calculations that I would have would be a lot more than, in other words, it's 5% having to do with the rating of the voltage of the equipment, not some voltage that keeps moving all over the place that you can't even work from because it's not. We know you're supposed to have 230 at 230 volt piece of equipment. So if I use my logic there, 5%, what is 95% of 230?
218.5.
What is it?
218.5.
So what is 218.5 minus from 240?
21.5.
So therefore, I would calculate my voltage drops at 41.5 volts. Let's try this again. 230 volts at 90%. No,
90
I'm
is at
sorry. No.
95.
230 volts at 95% would be a 5% voltage drop effectively at that equipment, right?
Yes.
Right.
Okay, but if I apply 240 volts, then what is that voltage minus 240? 95% of 230.
228.
Was it?
240 is 228. Voltage drop, 5%.
Okay, so it's 228.
The other one is
No,
218.5.
230. Did I say 240? I apologize.
We
I'm
said
sorry.
230 at
230
95%.
volt piece of equipment, and I want to go 95% of its rating.
It's 218.5.
That's 218.5. I'm going to, however, I'm going to have a 240 volt supply. Happen to have a 240 volt supply. Just happen to be. Then what's that between the 240?
21.5.
So therefore, I would calculate
Nine.
my voltage drop at 21.5 volts. And that would make sure that my equipment has a voltage not less than 5% of its rating. Rather, listen, here's my point. You start working this 2% and 3%, the size conductors you're going to have in any kind of large building, it's going to be impossible. And it serves no purpose for anything there. So I'm going to move on, but Mario, anybody else want to say something? We'll move on. All right. Okay, effects of voltage drop on resistive loads. Eric, you brought out something I really pay attention. Reasonable efficiency of operation. Okay, well, what's the effect on a resistive load? Conductive voltage drop can cause resistive loads like a water heater, an electric lamp, even an incandescent light bulb to underperform what would be expected. Yet they will have a longer life. Here's an example. The actual power of a piece of equipment is a function of its rated power times the relationship between the actual voltage and the rated voltage. Because voltage has an effect. Let's get this example here. If I have a 4,500 watt water heater, how many watts will it consume at 230 volts? 4,500 watt water heater at 230 volts, how many watts will it consume?
4,500.
Guys, you're into the question. Take a look at listen to me, look at me. 4,500 watt water heater connected to 230 volts. How many watts will it consume?
4,500.
Mario, put down your calculator.
4,500
you very much.
watts.
4,500 watt water heater at 230 volts will consume 4,500 watts. As you drop the voltage down, we have to understand something because I is equal to P over E, right? As you drop your voltage down, then you're going to end up having, or P is equal to E squared, whatever. P is equal to, whatever. The power is going to get less on a resistive load. Can't think of the formula right now at this instant, right? Now, what I'm saying is as the voltage goes down, power goes down by the square of the voltage. So if you go to 208 or 220 volts, you got a water heater rated 230, but you connect it to 220 volts. Well, you take the voltage change and you square it. What's 220 divided by 230? What is that 220 divided by 230? In other words, I'm now applying what percent voltage?
0.9.
What percent? 90%?
Yeah.
So I get 90% voltage. And if power is by the square of the voltage, if you go down 90%, Eric, the square of 90% is what?
81.
81%. So the energy I'm going to get is going to be 81% of the energy. So a 4,500 watt water heater is not consuming 4,500 watts at 220 volts. It's consuming what? Right there. You take that square at 91%. I'll probably add another line there. It'd be 4117. It just so happened about a week ago, I was in my little room there on the side of the house, Brian, where I have my fishing gear and everything like that. I looked at the water heater, and I looked at a nameplate rating. It just happened to catch a cough light, and it gave me the power at 230, and it gave me the power at 208. And I'm like, and it was like, let's go with this, guys. If it gets 4,500 watts at 230, what is that water heater connected at 208?
$36.80.
3680, because we took the 208 divided by the 230, and that is what percentage? 208 was what percent of 230?
90%.
No, it's not. 220 couldn't have, 220 was 90%.
It was 95%.
Oh, it was 95%.
Yeah.
220 was
Right.
95%.
Yes.
Squared, okay.
This one's 90.
220 is 90, so 95%. Eric, what's 95% squared, or 95.95? The one the 220 over 230 would have been.
9,025.
It's 90. It's
Oh,
very,
it's not.
very close to
That's
90.
90% was the answer. I gotcha. But 208 over 230 is going to be
90%.
90%. And then when you square 90%, it comes out to be 81%. And
Right.
that's when you said, Eric, it came out to be 3,000.
3680. Where this really comes into play is a 240 volt heater working on 208. That's 75%. So
Now-
10 kW heater rated at 240 is 7,500 at 208.
Did you follow what he just said? Because, okay, let's see if that's true. Take this 10 kW at 230. Let's do the math. Take the 10 kW at 208. I like that as an
I'm saying
example.
240. If I'm using 240.
I'm sorry. Oh, you're using 240. 10
Right.
kW 240.
10 kW at 240 is 7.5
Okay, but
kW
that's
at
right.
208.
Okay, take 208 and 240. What's that percentage? Just 208 divided by 240. Ken?
That was 9%, wasn't it?
87%.
And then what's the square of 87%?
75.11.
75%. Okay, so just kind of giving you some concepts that it's possible you get a piece of equipment, you're a contractor, and they're buying this piece of equipment, and they're hooking up to something that they would expect a toaster to be creating a certain amount of heat. This extrusion plastic thing. In other words, you look at the nameplate, and the thing is rated 208. And you're in a 240 volts. I mean, you're in a 208 volt system. The equipment's rated 208. I mean 240. Well, 230. Well, you're not going to get the heat, Brian.
Well, I ran into this, because it applies to this, an issue on a generator installation. We had done actual loads, and it was a very high utility voltage. It was at 246 point something. We sized everything based on actual.
Okay.
Installed the generator, and this particular generator came from the factory set. It was just a tad under 230, actually. And I bumped it up, I think, to maybe 235 or something like
You
that.
can bump up a generator?
Yeah, a little bit. I mean, not a significant amount, but
Okay.
a little bit. This was not a Generac, it was a different brand.
Okay.
Installed everything, started it up, everything was just fine. And then we started getting phone calls. Lots of phone calls. Because it was in a type of a manufacturing facility. And because the utility voltage was so high, and the generator voltage was not, and they worked with resistive heaters a lot, all of the calibrations on all of their equipment was off when they were on generator. So literally production had to stop if they were on generator, which was the whole purpose they bought the generator initially, was so that if there was a power outage, they could finish, because they were involved in heating products, they could finish whatever they were working on. And it was a pretty complicated scenario to get it sorted out. We ended up having to get the generator voltage up real close to the utility voltage, which was a process.
So the problem was they were used to a very high voltage that would
Yes.
not be normal.
Everything was calibrated, all their timing, and this is a bigger facility, so it's not like they can just go in and turn a dial and fix it.
Was this something you got a phone call and you instantly knew what it was?
No.
Or you took you a while to figure out?
No clue. I could not. They just said, "Hey, there's something wrong with your generator," because none of our equipment is operating properly. We're having issues, and it actually honestly took them about a week before I was ever really able to get engaged with them to figure out what their process issue was. And then they said, "Look, the equipment's not heating right. We don't have enough amperage." And I didn't even catch it then.
Right.
And so what happened, right? I'm then taking amperage readings on utility and then switching to generator. And then I'm looking and going, oh, I know what the problem is, a week and a half later.
But think about this. If you don't understand this basic fundamental concept that we cover in electrical theory, right?
Right.
You're supposed to be the guy. Right? You're the guy. You're the contractor. You're the leader. You're the journeyman. You're supposed to be able to walk in there and say, "Wait a minute now, this voltage is lower than the voltage you're used to." Boom.
When we had engineers and manufacturing engineers, everybody
The
was trying to
equipment
figure
guys,
out.
everybody going crazy.
Because it was such a complex thing.
Well, what you could have done is take the voltmeter, okay, at the load. All right, the switch up. There you go. You know the heat. You said it what? It was 240. Let's do the math here, guys.
That was about 246, 247.
246, and let's go with 230. So
Yep.
let's say 230 and 247.
I think it was actually a touch under 230.
I know, but I'm
truthfully.
saying 230 and 247. That gives me how many? Like 230 divided by 247 squared, right?
87%.
87%.
So 87% is the heating they were getting out of the process.
And they were dealing with plastic. And so the temperature is critical when you're dealing with plastics.
Okay?
And just one more. The other reason this is so critically important is that contractors need to know this is because of apartment buildings. Because a lot of times what happens is you have 240 volt rated equipment and the apartment is 208. And so the heating elements are operating at 75%.
My water heater takes longer to heat up.
Right.
My electric heater, I turn on my heater in the wintertime and it doesn't get that hot. So I bet you if you look at the nameplate of a electric spacing equipment,
240.
it'll be different voltages and it will give you different kW ratings. It's a 5 kW heater at this voltage. It's a 7.5 kW heater at this voltage. It's a 10 kW. At 240, it's 10 kW. And what is it at 208?
7.5.
7.5 kW, just like you just said. All right, let's move on. Wanted to put this in light to recognize the effects of voltage drop. Okay? Effective voltage drop on inductive loads. Conductor voltage drop can cause inductive loads, motors, electronic loads to overheat, be less efficient, and have a shorter lifespan. So if you drop the voltage, you could actually cause equipment to be getting a little warm. An extreme example of a voltage drop is I was doing some work at my house. I purposely was trying to design something so that I could lose the neutral to the building, but use the earth as a return path. The result was my voltage on my circuit that had my electronic ballast. I wiped out 3 of the electronic ballasts. I had not considered the effect of voltage drop, extreme voltage drop, on those electronic ballasts. Opening a neutral of a circuit, your lights get brighter and dimmer. Well, that's the way it used to happen. Now you have all these electronic LED drivers, and you have electronic lighting, and you lose a neutral now, and you go to 180, or you go to let's say you go to 160, and you go to 80. We're not just making difference in lights. You're starting to wipe out things, surge protection devices, AFCIs, GFCI breakers, receptacles. They're getting overvoltage. They're electronic. They're getting toasted. Brian.
Well, we, and this goes back a number of years, but we used to do analysis of power on theater facilities, and brownouts were a big issue where there were power dips on the early computerized lighting control systems and sound systems. It would almost invariably, it would fry something almost every single time.
Okay, so These are extreme cases, not really voltage drop, but understand the effects of voltage and changing in voltage. Inductive resistive load. All right, here we go.